Unlike the first two examples where we saw potential energy as a means of a position, there is another kind of potential energy known as elastic potential energy, which is associated with springs. So imagine where we pull a spring a certain distance, we let it go, it starts to oscillate between 2 points. That is due to some kind of potential energy that the spring has when it changes from the equilibrium position. It still says that mechanical energy at one point is the mechanical energy at the second point, so this is still what we know as K1 plus U1 has to equal K2 plus U2, but now U is the elastic potential energy, which is given by 1/2 the spring constant K times the amount of stretch x squared. So this is going to be 1/2 mv1 squared plus 1/2 kx1 squared has to equal 1/2 mv2 squared plus 1/2 kx2 squared. K1 is where the spring is just before it's released, so that is 0. And so we have that K2, if we solve for the speed, is going to be U1 minus U2, which is 1/2 k x1 squared minus 1/2 k x2 squared. And we can plug these values in. We can actually factor 1/2 k, that probably is better. And we get 1/2 k times the quantity x1 squared minus x2 squared. So this is 1/2. K is 5 newtons per meter times x1 is the amount of stretch at originally, which is 0.1 meter quantity squared, minus the second distance, which is 0.08 meters quantity squared. So that tells us that K2 is about 0.009 joules. And as we know, if we want to find the kinetic energy, it's equal to the mass times the velocity squared. So V at that point is going to be the square root of 2k over m, which is the square root of 2 times 0.009 joules over the mass, which is 0.2 kilograms, and that gives us a speed of plus or minus, remember, 0.3 meters per second.